Okay, so here we have a question that deals with electric forces and fields inside some conducting plates. And we are trying to design an experiment to learn about what's going on. We're given some list of supplies, and we have to pick how we're going to do that. All right, so this question is tricky to give an answer to because there are multiple answers. I'm going to talk, I think, about the two ways that I can think of that are pretty good, but it doesn't mean that they're the only two. So keep that in mind if you're paying attention to this. So the first thing we have to do is kind of answer parts A, B, and C all together, right? Because we can't know what we're going to use until we know what procedure we're going to try to follow, and we won't know how we're going to use it until we know what we have available and what we're trying to do with it anyway. So it's really doing all those parts at once. I personally, if I was doing this question, would probably actually start with part C, and then as I ran into things that I needed, I'd put a check mark by it, and then sort of make my diagram that fits what I'm trying to use. So I'm going to start with the procedure, at least generally. So we know we have two charged plates, right? Two large charged plates, right? 1 and 2. That's kind of sloppy. Like so. And then in that area in between, right, this is a capacitor. So in that area in between, there's a uniform electric field. We don't know which way it points, but we do know there's a uniform field inside. And we're given a charged ball attached to an insulating string, and we can attach it to whatever we want, right? That's what the stands and clamps are. So if we take that charged ball, right, and hang it right in above the plates, because it's charged, it's going to feel a force, and it's going to get deflected to one side or the other. Right? So I'm going to draw it this way. It doesn't mean it has to have gone that way. It depends on which plate is which charge, right? But it's going to get deflected one way or the other. And how much it's deflected, we know is related to the electric force, right? A stronger force means a bigger deflection of the string. And we know how the electric force relates to the electric field. And so this is going to be kind of where I start on how to figure out how to do this. So if we knew how much it bends, we know how strong the force is. And what that means is that we really want, right, like this angle right there. If we could measure that angle really well, then we could figure out the tension force that's vertical and horizontal. We know the weight of the ball, so we can figure out that equilibrium condition, and then we can solve for the electric force and therefore the electric field. So that would be one option. And so how do we go actually about measuring that? I would say that what we need is a protractor and a meter stick. And the reason we need a meter stick is that, is that this this vertical line, right? It's not really present. We can't see it. And so if I was going to do this, I would hang the meter stick, right, from like a point, and so it hangs vertically, because a wooden meter stick is not going to get deflected. And I do that wide, but if you hang it like the narrow way, actually maybe I'm going to actually do that, right? If you hang it like the narrow way, then that would hang vertically, perfectly vertically, and that gives us something we can measure the angle between, the string and that. And so then I'd put the protractor, up here, right, kind of like that, right? And so that way I could measure the angle, right? So this would be sort of one experimental setup that I could think of that would work. I measure the angle, and I'm going to get to the calculation and procedure stuff, but I kind of just talked through it. That's setup number 1. Setup number 2 is very similar, right, with one slight difference. So in setup 2, instead of measuring the angle, I'm just going to create another force that's much easier for me to measure and compare them. So I'm going to hang the ball just like before, and after it hangs and sort of deflects out by that angle, rotates over a little, then I'm going to attach the spring scale to it. And I'm going to pull back on the spring scale until it's perfectly vertical. Right? And once again, to know what perfectly vertical is, I'm going to hang the meter stick sort of thin ways right there, right? So it's vertical. And then I'm going to go until I see the string that the ball is hanging from that's exactly parallel with the ruler. And I'm going to have the the spring scale right here attached to it. And then I'll read what this value is, F spring. That's required for me to pull it back to being exactly a vertical hanging ball. Right? Either of those will work. And so for setup 1, it's going to be meter stick and protractor. Right? And for setup 2, it's going to be meter stick and spring scale. I think that if you had there would be a third way you could do it, but it would be a real pain because it's at an angle. But you could have like a stopwatch, right? You actually wouldn't need the stopwatch. You have like a slow motion camera and see how long it takes to cover a certain distance and try to calculate the constant acceleration that way. That's going to be tricky because as it rotates around, some of the forces are going to change. So I don't think that's a good idea, but I think it's possible. I think these are the two really good options. All right, so let's get to. I think actually kind of talk through the procedure, right? I'm not going to write that down. If you want to know, listen to the video again. So now we're going to the side of things. So how do we calculate the magnitude of the electric field? So for setup 1, it's right. We get a free body diagram of the ball that looks something like this. Right? Maybe everything's kind of flipped around, but it's going to look kind of like that. And so we can say it's in equilibrium. So we get, and we know this is the angle theta that we just measured. So we know that T sine theta, that's the horizontal component, negative plus Fe equals 0, which tells us that, actually, I don't want to do it that one. Which tells us, since we know what the relationship between force and field is, that T sine theta is QE, right? Q is the charge on the ball. And so the electric field is T sine theta over Q. We don't know the tension, but we do have a bit more information, which is that T cosine theta minus mg equals 0. So we can solve this to get T equals mg over cosine theta. And substituting that in, we get mg tan theta over Q. Tells us the strength of the electric field. The direction is actually a lot easier, right? If the charge is positive, whichever plate it moves towards is the negative one. Well, actually, sorry, that was part 3. Part 3 is the easiest one. Whichever plate it moves towards is the negative one, the other one's positive. How do we determine the direction of the electric field? Well, we know that since our thing is positively charged, the direction of the electric force and the direction of the electric field are exactly the same. So in this diagram right here, right, the electric force points to the right, so the electric field also points to the right. You could also actually use part 3 to say, well, it's deflected towards the negative plate and the electric field points from the positive plate to the negative plate, and so the electric field sort of points in the direction of the one that it moves towards. That would be another way you could kind of explain them together. And then finally, I'm going to just go back and talk. Right, setup 2. Setup 2 is actually easier to do the math with. So setup 2, how do we determine the electric field? Well, we know that F spring equals Fe. So F spring over Q equals E, right? And we're done. And then the other two parts are exactly the same. So the second experiment is, I think, actually easier computationally. and possibly even easier to do. But both work perfectly fine. The key is if you're doing this, write a very clear procedure, indicating exactly what you need to measure and how you're going to measure it. And if you've been watching this whole video for a review for the test, if you want 1 bonus point, write the word cat somewhere on your test, and I'll give you a bonus point since I know you were reviewing.